Thank you, Amri, and I'd like to thank organizers for the invitation and welcome all of you. So I will begin with some basic notations. So G will denote the finite dimensional simple Lie algebra. So for simplicity, I am considering only finite dimensional simple Lie algebra. And P plus denote the set of dominant integral weight of G, and V lambda denote the irreducible integrable G module of highest weight lambda, and W with the Weil group of G and Q with the root lattice of G. We'll define what is called constant Kumar modules. In short, we'll call it a KK module. So these modules were first formulated in the context of strong PRV conjecture due to constant, and this conjecture was proved later by Shrawan, Kumar and Matthew independently. So what are these modules? So let W be a Weil group element and V lambda be the highest weight vector of V lambda, and VW mu be a non-zero weight vector of one-dimensional lattice space of weight W mu inside of V mu. Then the cyclic submodule of the tensor product generated by V lambda tensor VW mu is called the KK module, and it is denoted by K lambda W mu. Here is some quick properties of the KK module. If I take W is equal to identity element, so this will be isomorphic to V lambda plus mu. And if I take W is equal to the W naught, that is longest element, that will be equal to the full tensor product. And if I have a W is less than or equal to W dash in Bruha order, then KK module corresponding to W contained in the KK module corresponding to W dash. And also here is a, if I switch lambda and mu, so K lambda W mu is isomorphic to K mu W inverse lambda mu. So W will be W inverse. So this property shows that this the tensor product, the KK module gives a filtration of this tensor product, which with respect to the Bruha order in W. And also here is one more property. If I take a two element W and sigma such that their double cosets are same, then the corresponding KK module will be also equal. So we know that since this is a finite dimension module for G, then it will decompose into the irreducibles. So if we write the decomposition of KK module in terms of irreducible, so let C lambda mu nu W denotes the multiplicity of V nu in the KK module. So let's denote C lambda mu nu as it had been denoted before also. It's a multiplicity of V nu in the full tensor product. So note that if I take W is equal to W naught, since the KK module will be the tensor product, so that is equal to C lambda mu nu. That's a multiplicity. So here are some properties of this tensor product multiplicity with W. If I take the W is equal to identity, this is just the Kronecker delta, that is delta lambda plus mu nu. And if I take W is less than or equal to W dash in the Bruha order, then the corresponding this tensor product multiplicity is smaller than C lambda mu nu W dash. And if I switch this lambda and mu, then here W will turn to W inverse. And this will also imply this one, but this one we already know that. And if the double coset for W and sigma is same, then corresponding the tensor product multiplicity is equal. So here is a one example. If I take Z is equal to SL3C, then the Weil group is just S3. And if I take a two dominant integral weight which correspond to the partition, take lambda and mu is equal to 210 and mu is equal to 320, then the tensor product multiplicity, this C lambda mu nu in full tensor product is 2. But if we see this refined multiplicity, if I put here S1 and S2, this is 1. And S2, S1 it is also 1. For S1 it's 0, S2 is 0, identity is 0. So in the Bruha graph you can identify, we can draw all this picture. Okay. So let me give one more characterization for this refined tensor product multiplicity in terms of Lakshmibai Seshadri paths. So yeah, so these Lakshmibai Seshadri paths were introduced by Littelmann. He was motivated by the work of Seshadri and Lakshmibai on standard monomial theory, as Sagaki already mentioned in his talk. So what are these paths? So these paths are the piecewise linear paths from close interval 0, 1 to P tensor R. So here P is a weight lattice. We are just taking the extension scalars I am extending by R. So if I take a mu in a P plus, then a pi in a pi is if the LS path pi of shape mu is given by this sequence. So these are the some sequence W1 bigger than W2 WR, where these WIs are the left poset of W mu. Here W mu is a stabilizer of mu, and this some bunch of rational numbers between 0 to 1. So this is not just a random sequence. There are some relation between these WIs and AIs that's called chain condition, which I'm not explaining. There is some condition, and this pi is denoted. It is defined this way, that if T belongs to AS minus 1 to AS, then pi T is defined this formula. So if you notice that, you can see that this path is piecewise linear, like from interval 0 to A1, it is going in W1 mu direction. After that, it is going to W2 mu direction, right? So it is going piecewise linear. So the first direction, that is W1, we call it the initial direction of pi, and the last direction we call it a final direction of pi. And let P mu denote the set of all LS path of shape mu. So why these paths are important? So one Littelmann proved that this gives a path model for the tensor product. Like if you take a V lambda tensor V mu, then you take all these paths, all these tuples in P lambda tensor P lambda cross P mu, where P lambda is the set of all LS paths of shape lambda, and similarly mu. Then the character of the tensor product you will get by e power just pi 1 and pi dash mu, where pi 1 is the end point of path and pi 1 dash is also end point of path. We just add that, it will land in the correct weight. No, end points will come the weight. Wi mu, Ws mu. Right. Okay, so we also give a path model exactly in the same spirit, the path model for the Costa and Kumar models. What we do for a given pair, pi and pi dash, we associate a well group element that is denoted by script W pi pi dash. Then we single out this subset P lambda W mu, such that collection of all these pairs such that association well group is less than or equal to W. Then you sum over all these pairs in this set, that will give the character of KK model. Okay. So now we give a decomposition rule for KK module in terms of Lakshmibai Seshadri path, and this decomposition rule is given by the Joseph. Let me explain that. What is this? So for given any lambda in P plus and LS path pi of shape mu, we call this path pi is a lambda dominant if lambda plus pi T is dominant is in the dominant chamber for all T. Then let's this notation is little heavy notation. So the P mu upper lambda W is bigger than W U is denoted that collection of all path pi such that pi is a lambda dominant and the initial direction of pi is less than or equal to W mu, and the final direction of path pi is bigger than or equal to W mu. Okay, so I'm putting the both conditions. So what is the decomposition rule? That the KK module K lambda W mu is just isomorphic to the direct sum of V lambda plus pi 1, where this pi show up from here. So pi belongs to pi mu lambda W, and here I am putting the identity. Putting identity means I am not putting the condition on anything in the final direction. I am saying the final direction is bigger than identity, bigger than or equal to identity, so every path will work. Okay, so let's denote this is, I am going to introduce one more thing in this notation. So say E mu lambda W bigger than U colon nu, where nu is a weight. So I am just taking all those paths such that lambda plus pi 1 is equal to nu, such that lambda plus pi 1 ends up nu. So now you know that this multiplicity, this tensor product multiplicity in KK module is just the cardinality of this set with this is identity. Okay, so this is a giving some counting of this multiplicity in terms of paths, and this is also generalization of a decomposition rule for the tensor product. If I take here W naught, then it is just the same Littlewood-Cherson rule given by Littelmann. Okay, so here are some more properties. So there is another way I can count this refined tensor product multiplicity in terms of paths in another way. What is that? So let pi be an LS path of shape mu. So we are defining a pi dagger that is given by the Littelmann, that if I put here W naught, the first, then this order will be reversed, right? And then these rationals also I will just put by 1 minus of that, then this will be also reversed. So he proved that this pi dagger will be also an LS path of shape mu. And this dagger map from pi mu to pi mu, p mu, it will be an involution. And also, if we observe closely, that if I take a path pi in this set, that is, it is the path of shape mu, which is lambda dominant, initial direction is less than or equal to W, and there is no condition on final direction, and suppose it ends at nu, that is lambda plus pi 1 is nu, then pi dagger will be again a path of shape mu, but now this is the nu star dominant. And there is no condition on the initial direction, but final direction will be bigger than W naught W, and the nu star plus pi dagger 1 is equal to lambda star. It ends at lambda star. So these two have the same cardinality. So this, instead of counting this, I can count this also, and that will also give the one characterization of the one counting of this tensor product multiplicity C lambda mu W. And if I put W is equal to W naught, then note that this inequality will get in the full tensor product, which we already know that. Okay, so here is one more property. So if I take a pi as a path of shape mu, then denote a pi star. So what is pi star? I am just changing all these W's in star, W1 star, W2 star, where what is star? Star of any W is just multiplying by W naught both sides. Okay, and this leave the scalars in the same way. So we'll see that this pi star will be the LS path of shape mu star, where mu star is minus W naught mu. And this star map will be just a bijection from P mu to P mu star. And it also gives a bijection from the P mu lambda W bigger than or equal to 1 to P mu star W star bigger than or equal to 1. So from this, we can conclude this relation, that C lambda mu nu W is same as C lambda star mu star W star. And that will give this inequalities also. And is another property, that if I take I is a subset of S, where S index the nodes of the linking diagram of G, and let Hi denote the subspace generated by these co-roots, where I is in capital I, and let mu is in H star, then mu I denote the restriction of mu on Hi, and let Gi is the subalgebra generated by Hi and these Ei's of I, the generators. In general, these Gi's are semi-simple, right, if it is not connected. So this whole theory that Littelmann LS path is all defined by the symmetrizable Kac-Moody algebra, all these things. But for simplicity, I have considered just the simple Lie algebra. And let Wi denote the collection of all Weyl group elements such that the support of W is contained in I. So where what is the support of W? You write any reduced expression for W, whatever simple reflection shows up, that collect that I is in S, that is in the support of I. So this Wi will be just some correspond to the Weyl group of Gi. And let Qi denote the collection of all alpha in Q such that the support of alpha is contained in I. What is the support of alpha? If I write alpha into the sum of simple roots, then I am collecting all these indices where Ci's are not equal to 0. Okay, so we can notice these inequalities, that if I take lambda mu in P plus and W is in the Weyl group element, and suppose I is the support of W, then C lambda mu nu W is just the delta lambda mu nu W, where and C lambda I mu I nu I, so these are the lambda is like a restriction I define here, and this W Gi. So here Gi I am just putting to emphasize that it is I am considering as a Lie algebra Gi. Where what is this delta term? This delta lambda mu nu W is 1 if lambda plus mu minus nu is in Qi. Otherwise, it is 0. This term just comes from the technical reason that sometimes this can be 1, but we cannot arbitrarily extend anything new, right? We have to just put that, so it should be in the root lattice, right? So now we can notice one more inequality, one more property of this C lambda mu W, that if W is a well group element, I is a support, and now I am now breaking this I into the connected component of I, and let Wj denote the Wij, then W I can write down product of this little Wj, where each Wj is contained from Wj, and this all will commute because it's coming from the connected component. So different things will commute. And let Gj denote the Gij, Hj denote the Hij, and similarly here lambda mu nu for any weights for G, lambda j mu j nu j denote the restriction on Hj. So we can notice this inequality that C lambda mu nu W is same the delta lambda mu nu W is equal to product of C lambda I mu I nu I Wi Wj Gj. Okay. So now I am going to define what is called the saturation and semi-group property. So an element W is said to have a saturation property if the following holds for all lambda mu nu in P plus. That for some integer k bigger than or equal to 1, if C k lambda k mu k nu W is positive, then C lambda mu nu W is also positive. And we can define the semi-group property that an element W is said to have a semi-group property if, again, this holds for all lambda mu nu, that if C lambda mu nu W is positive and C lambda dash mu dash nu dash W is positive, then addition of this C lambda lambda dash mu dash nu dash W is also positive. Okay, so we will see which elements have these saturation and semi-group properties. So there are some obvious candidates, like if I take W is equal to identity, this obviously have both properties, that saturation and semi-group, because this is just the Kronecker delta. Okay, so in this case, these two are equal, and obviously it will follow that it has a saturation and semi-group property. And in the case when G is the type A, then these constants are called Littlewood-Richardson coefficient, and for W naught, the W naught have saturation and semi-group property. This is proved by Knudsen and Tau by using their honeycomb model for C lambda mu nu. And in this case, we call it this C lambda mu nu W is the refined Littlewood-Richardson coefficient. And we prove that this the saturation and semi-group property true again for some special class of permutation of W. Okay, so what is this special class? These are the pattern avoiding. So now we'll take G is equal to SLNC, that in type A case we'll fix to SLNC. In this case, the well group will be just the symmetric group Sn. So a permutation is called 312 avoiding. So when a permutation W in Sn is said to have contains a 312 pattern, if there exist indices I less than j less than k such that Wj is less than Wk is less than Wy. And a permutation not containing any 312 pattern is called 312 avoiding. So for example, if I take this permutation, W is equal to 4, 5, 2, 3, 1 written in one line notation, is not 312 avoiding, because if I take indices 1, 3, 4, then I notice that W3 is less than W4 is less than W1. So it contains a 1, 3, 1, 2 pattern. It is not 312 avoiding. On another hand, if I take W dash is equal to this permutation, then it is 312 avoiding. It doesn't contain any 312 pattern. So similarly, we can define any kind of pattern avoiding permutation. So similarly, we can define 2, 3, 1 avoiding permutations also. So we need only these kind of avoiding permutation. So a permutation in Sn is said to be in a special form if it is of the following type. If W is either 312 avoiding or 231 avoiding, or if W is a commuting product of such element, right? It is coming from the Young subgroup and W is equal to W1 Wp, where each Wi's are either 312 avoiding or 231 avoiding. So what we have proved that if permutation W is in a special form, then W has saturation and semi-group property both. And now we'll build. I will give some comments of that. That if it is enough to prove saturation for only this first kind. The second kind, for the second type of permutation, it just implies by this formula. Okay, if this all these Wi's has a saturation and semi-group property, then obviously W will also have, because we have this formula. Okay, and for n is equal to 1, 2, 3, that all Sn have a special form. So for the small symmetric group, obviously it's true. For n is equal to 4, all permutation are either 2, 3, 1 avoiding or 3, 1, 2 avoiding, except these 4 permutation. So for these 4 permutation, we don't know whether it has a saturation or semi-group property, but for all others is in the special form. So those things we know. What? Yeah, I expect it is holds for all. Just addition. Okay. There should be some connection, but means I don't know the geometry version. I work means those things means in terms of Schubert variety, I cannot answer means. Okay, so here is some comment about if we look for other types, right? So it is just a type A case, but I'm restricting in other diagram in type A case. So what is that? So if I take if W has a saturation or semi-group property for ambient Lie algebra G, if and only if W, if I consider as a Weil group element in GI, have a semi-group property for G. That's just follows from this formula. So if I take a W is a Weil group element and I is a support of W, and suppose I be any type A subdiagram. Okay, I is just taking in a type A subdiagram of G, and if this W is a special form in this WGI, then this W has a saturation and semi-group property for G. So we can say it is just a type A case, but we can say in some other type also, those permutation have a saturation and semi-group property. Essentially, it's just a type A. Okay, so now I will introduce means what is Hive. So already Hive has been introduced in the first talk. So let's see some more Hives. So now we consider G is equal to SL and C, and in this case the set of dominant integral weights correspond to the integer partition with at most n parts, and take lambda mu nu in Pn, and with this relation then Hives are this big Hive triangle with n plus 1 vertices if I working in Sn. Then the left edges is left boundary is labeled by the partial sum of lambdas, and bottom is labeled by the partial sum of mu i's with mod lambda, and right boundaries are labeled by the partial sum of mu i's. And between these I have to fill with real numbers with some conditions. So what are those conditions? We can notice that there are 3 kind of rhombus here, that this red one, the right slanted, left slanted, and some vertical. So there is a rule to fill it, that we have to, if these labels are some A, B, C, D of some rhombus, the rule is we define a content of a rhombus that the sum of obtuse labels minus sum of acute label, that is B plus D minus AC. This rule is for any kind of rhombus. So we have to fill with the integers such that the content of each rhombus are greater than or equal to 0. By this condition, if I collect all these fillings, that will be a polytope, and that we call it that is called a Hive polytope, that and denoted by H lambda mu nu W. So here is one example. If I take lambda is equal to 2, 1, 0 and nu is equal to 3, 2, 1, then this Hive polytope, so the left side is just labeled by partial sum of lambda, and this is just a partial sum of mu, and right is nu. Then there is only one free variable, and if I just calculate, work out all these rhombus inequalities, then we find that this has choice only the closed interval 4 to 5. So it is just this hyperpolytope. And Knudsen and Tau proved that the number of integral point in the hyperpolytope is equal to the LR coefficient. So here we can notice that there are only 2 integral points. So in this case, this LR coefficient is just 2. So this is a Hive model for LR coefficient. So similarly, we want to find out a Hive model for the refined LR coefficient. Okay, so let's see what are those. So for that, we need some setup. So let's denote the big Hive triangle, and this script R be the collection of all small rhombi of all 3 kinds, left, right, or this vertical, all collection I am taking. So for given any rhombus, let VR denote the set of all 4 vertices. And for a given any subset of this, we'll denote VF is just all the vertices in F. Okay, it's a union of VR are in F, just containing all the vertices in F. And now we define a frozen subset. So what is a frozen subset? It is defined recursively. So for a given F in F is a subset of R, it is called frozen. If its cardinality is 1, then it has to be one of this above type. Okay. If its cardinality is more than 1, then there exists an R in F such that you remove that R, then the remaining thing is frozen, and the obtuse vertices of R belongs to the vertices of H union boundary. Okay. So here are a few examples of frozen subsets. Like we can take, in particular, take this one. So this is a frozen because we can just keep removing. If you remove this, then you know that this is in the obtuse vertices. This one is a boundary, and this is the previous one, and the remaining will be still frozen because now we have to go by induction. Then remove this, then remove this, remove this, remove this, then we'll land F here. So these are all the kind of different kind of frozen subset. And now comes the main theorem. So what is that? So we call it a rhombus R is a flat if its content is 0. Okay, so the condition on this Hive is content will be always bigger than or equal to 0. Now we are calling it is a flat if content is equal to 0. So for given any Hive, we denote the flats of S is the collection of all rhombus any kind such that R is flat in H. Okay, so for given any subset F of R, we define a face of Hive polytope is denoted by Hive lambda mu nu colon F is equal to collection of all Hive in the Hive polytope such that F is contained in the flats of H, and denote by this Hive Z lambda mu nu F the set of integral points in this face. Okay, so what we can prove that if F is a frozen, and if this Hive face for this frozen face is non-empty, then it contains an integral point. And the proof is just the proof by the Knudsen and Tau. We adopt the same proof and we apply in our case. It works in the frozen case. Okay, so it's just the essentially same technique. So let me define what is called Hive Kogan faces. So now we focus on this only the northeast rhombus and the southeast rhombus. So let's northeast rhombus is labeled by that this top is R21, R31, R32 like that. So let NE bracket script R is denoted by that, and SE bracket R denoted by this right slanted, that southeast rhombus. So for any F is in the subset of northeast rhombus, this face is called Kogan face for Hive polytope. And if H is in the southeast rhombus, subset of southeast rhombus, this face is called Duan Kogan face for this Hive polytope. And also just label this rhombus means Rij and Lij both labeled by Si minus j. So okay, so just label by Si minus j, then it will appear like that. So for given any F is the subset of northeast rhombus, we define sigma F is equal to the product of Si minus j when Rij in F in the lexicographic order. So for example, if F1 is given by this 2, 1, 3, 2, 4, 3 and 5, 2, 5, 3. So these are the things. So the product of this is S1 multiplied with S1 just identity. The remaining is just S1, S3 and S2. And here also you will get S1, S3 and S2. So for different kind of subset will lead to maybe the same permutation. So if length of sigma f is equal to the cardinality of f, f is called the reduced. Okay. So you notice that the f1 is not reduced, but f2 is reduced. So we are following this whole construction is given in the Fujita paper. So we are just following the Fujita notation. Define that for a given f, define the omega f is equal to w naught sigma f w naught. And for a given permutation in Sn, hive lambda mu nu w is equal to union of hive lambda mu nu f, where the union is taken over all the reduced phase f such that f is the subset of northeast rhombus and the omega of f is equal to w. Then we prove that the number of integral points in this hive lambda mu nu w naught w is equal to this refined tensor product multiplicity. So this is a hive model. So notice that this in general, this is just the union of phases, and the number of integral points in this union of phases is just equal to the this refined tensor product multiplicity. So this is the one hive model, you can say. So there is another way to get the hive model from the dual Kogan phases. So for a given h in the southeast rhombus, similar way we can, exactly the same way we can define sigma h, which we have defined sigma f before, exactly the multiplication of si minus j in the lexicographic order. And for a given w in Sn, now we are just denoting the bar to just make a distinction between that we are just taking union over all the southeast rhombus. So hive bar lambda mu nu w is the union of hive lambda mu nu h. Now the h varies over all reduced subset h of southeast rhombus such that sigma h is equal to w. Then also we get another characterization, this c lambda mu nu w is equal to hive z bar is, notice that here these things are changed. This is nu star mu and lambda star and w not w. And from this also we observe this inequality. So this is another characterization for another way in terms of dual Kogan phases. We have a model for this defined LR coefficient. Okay, so now we come to towards the proof that we take a hive Kogan phase. We see how the 312 works. That we see how the hive Kogan phase for 312 avoiding permutation looks like. So if W is a 312 avoiding permutation, then W not W will be 132 avoiding permutation. And in this case, there exists a unique phase in northeast rhombus that denoted by FW, such that omega of FW is equal to W not W. And it has the following shape, following type of shape. Means it will be always the right and bottom justified. And there is no hole in the middle. Means it will look like some inverted Young diagram, some shifted. Okay, so notice that this FW will be always frozen. This FW will be always frozen. This is the frozen. So in this case, this hive lambda mu nu W naught W is equal to, it is not a union of phases, it is just a single phase, because there is only one phase exists such that W bar WFW is equal to this W naught W. There is only one. So this is just a single phase. So the refined LR coefficient corresponding to W is just the integral point in this phase. Okay, so now this is just a single phase. So because of that, we are able to prove the semi-group property for 312 avoiding permutation. Like if we take W is equal to 312 avoiding permutation, then C lambda W, suppose these two are positive, then we know that there exists a unique FW of northeast rhombus such that there is an integral point in this hypertop. So these integral points are non-empty. There is a some point here and there is a some point with lambda dash FW. So what we do, we take some integral points here and that integral points here, you just add that. So if you add that, then this will also be flat on FW, because exactly it is flat on the same set, both H1 and H2. So that will also belongs here. So it has an integral solution. That means this refined LR coefficient for lambda dash, nu dash, this is also positive. In fact, we can say something stronger. We can say that this C lambda dash plus mu dash, nu dash W is always bigger than or equal to maximum of this and this, right? Because at least these many solutions will exist. I can take one here and add those. At least this many we can get. Okay. Now we can also prove the saturation property, that if W be a suppose 312 avoiding, and for some k, suppose this scaled version is positive for some integer k bigger than or equal to 0, then we know that there exists a unique k, FW of northeast rhombus, such that there is an integral solution. There is an integral solution with k. That means this hive is non-empty. Okay, there is an integral solution. So you descale by, means scale by 1 by k, you just scale by 1 by k, then boundary will reduce to lambda, mu and nu. And of course, we don't know about the interior, but there is, this shows that it is a non-empty because this is a non-empty. So this is a non-empty, this hive face is a non-empty, and since FW is a frozen, then it has an integral solution. That's what we proved that before. If it is a frozen and non-empty, then it will have a integral solution. So there is an integral solution for that. So then C lambda mu nu W is positive. So saturation is true, implying for 312 avoiding permutation. For 231 avoiding permutation, again we see the same phenomena for the dual Kogan phase side. So if W is a 231 avoiding, then W not W will be 213 avoiding. And in this case also, there exists a unique HW of southeast rhombus, such that sigma HW is equal to W not W. And this HW has this following form. It will be right and bottom justified with this shape. There is no hole in that. So note that this HW is also frozen. And in this case also, if we see this high bar, nu star mu lambda star W not W is equal to just one phase. And if I just calculate this integral point in this phase, that is equal to the LR coefficient. That's what we have noticed before. This is another model for the refined LR coefficient in terms of dual Kogan phase. So if W is a 231 avoiding permutation, then again if W is a 231 avoiding permutation and suppose these two are positive, then there exists a unique HW of it should be subset of southeast rhombus, such that this two has an integral solution with nu star and lambda star. Nu star mu lambda star, this has a integral solution, this will also has a integral solution because these two things are positive. And again you add those solutions, that will belongs here. So this has an integral solution, and now the number of integral solution in this is equal to this LR coefficient. So we have a lambda dash mu dash W is equal to positive. Now the saturation is also follows the exactly same way. If W is 231 avoiding and suppose this is positive for some integer k, then there exists a unique HW in the southeast rhombus, such that this k nu star k mu k lambda star HW is non-empty. Then okay, it should not be Z. It is just a high polytop. We just scale by 1 by k. Then this high phase, this is non-empty, and then it has an integral. Since this is a frozen, it has an integral solution. Then this is non-empty. Okay, so I have finished. Oh, I was fast. Okay, thank you.
Any questions? Yeah, there's a couple of questions there. Hi.
So maybe in this 231 or one of the cases in type A, and in one of the cases when you have the semi-group property,
Hmm.
do these generalized Littlewood Bridgerton coefficients have some kind of log concavity property as you scale them all by n, right?
That I don't know.
So, could you, maybe you said this, but could you say something about what so you don't get a polytope if W is not equal to W0, right? It's a union of faces in general.
Hmm.
So, so geometrically, is there something more that can be said? Like exactly what is the form of this polytope for different Ws?
Could be like it may not be convex. It could be some edges going inside. It could be some different union of faces. Like it's not convex. Yeah, it's a, could be very complex.
And what is the intuitive explanation for this frozen condition? I mean, you gave an inductive definition, but is there a more direct way of understanding what this frozenness means?
Frozenness means intuitively that we were looking the same condition which we used to prove the Knudsen and Tau conjecture. That means he showed that if there is a, if you get a hive which doesn't have any increasable subset and it is a corner, if it is a corner of hypertop, then all interior vertices is also the integral linear combination of boundary vertices. So we were looking for the same thing, like if suppose if you take this set, so here if some hive have this kind of shape like flat in this thing, then it doesn't have in means and collect this face, collect the face that which have only this face, this flat, then it doesn't have also any increasable height, that you cannot increase this. If you try to increase anything, it will mess up with the boundary. That's the intuitive things. So you cannot increase this because the sum of this should be bigger than sum of this. So you cannot increase this. If you increase this one, then you have to increase one of this. So if you increase one of this, then it will mess up with the boundary. So you have to increase either this or this. But if you increase this, you cannot increase because it is fixed by the lambda and mu. So you have to increase this. If you increase this one, then you have to increase either this or this, but both land up in the boundary.
I see.
So that's the main crux to defining this way to frozen things.
Thank you.
Any more questions? So I have one question. So if you try to define an algebra using these C lambda mu nu W, you fix W and then, so when is that associative?
How you define algebra?
So those are the structure constants. So you define an algebra with basis elements indexed by. So for example, when you take W to be this trivial, then you just get Schur functions, right? An algebra of symmetric functions with basis Schur functions. So, so is that going to be associative ever? I mean, it's not commutative. So, but would it be associative? In some special cases, it's associative. So you could ask for which permutations is it associative.
W naught.
Whatever, the full, but even
Full thing.
in that case, it's associative because then it's just, nah, yeah, whatever, what do you call it? The word algebra. Yeah. So both extreme cases, it's associative.
It could be.
No, it's not commutative. It is C lambda mu nu. W is C lambda nu mu W inverse. So if W is an involution, then it's commutative as well. So that's a good point. point. So then what about associativity? I mean, I don't know, just a random thing
Yeah.
that occurred to me. But any more questions? Okay, if there are no more questions, we can thank Mrigendra